I'm starting off with some material on the board because I'm having a bit of a problem with the camera, quite frankly. Dropped out. Instead of trying to break this one up into a bunch of different smaller particles, I'm going to try and see if I can keep this as one discussion. Now, at the beginning of each chapter, I might go back, or if you see me going back and hitting a couple of things we've done in earlier chapters, look on that as a good thing. What we're doing actually flows from earlier chapters, and the things we're going to do in the future flow from what we're doing now. We started with a discussion of forces. That's the first physics we do. In the first semester, we do some time with position, and the change in position is velocity, and the change in velocity is acceleration. Calculus, yes. Physics, not really. In my point of view, physics starts where we begin discussing forces. So if I've got, here is some particle, or a particle exists that has an electric force on it, that kind of, let us take that and let's look at what happens. Okay, suppose that wasn't there. How would whatever's providing this force, how is that affecting space in general? We've done this before. If I have this object here and I let go of it, I know, there'll be a gravitational force on it. So I can then say, okay, if there were a thing here, it would feel an it would gain an acceleration due to gravity of 9.80 meters per second squared toward the center of the Earth. That's a measure of the gravitational field. So we'll go to that more general form, from the electric force to the electric field. Now, to go from the electric force to the electric field is the electric force on a test particle divided by the charge of that particle. To go back in the other direction, the electric force is Q. The electric force on some point charge Q is equal to that charge Q times the electric field that it's in. Now, force was our first step in physics, but we didn't just stop there. We didn't even just stop with free body diagrams. Where this becomes really useful is by taking force and looking at force acting over a path gives us work, gives us energy. Force acting over time gives us momentum. For what we're covering this semester, energy is a much better way to track what's going on than momentum is. So if I've got an object that feels an electric force, and I move that object is going to feel a change in electric potential energy. So, let's see, if I'm going from the electric force to the electric potential, well, the change in electric potential energy is equal to the opposite of the work done, and the work done is equal to the integral over the path from the initial to the final position of the force integrated over that path. Now, I'm always going to start from this most complicated equation because it helps us never miss anything, and it often feels ever so good when we're able to simplify before we have to deal with any individual problems. Now, if I want to go from the electric potential energy to the electric force, well, the electric force on some object in the x direction is equal to negative the derivative, actually, I'm writing this as a partial derivative. Perhaps or perhaps you have not seen that yet. All it means is that if I take the partial derivative of the electric potential energy function with regard to, in this case, x. That simply means when I take the derivative of the potential energy function, I treat only x as being a variable. Now, let's look at what happens when energy, I'm looking at energy, not how energy is distributed among a system, but how it would be distributed if something else were there. So energy in space, as it were, and that is electric potential. Now, to get from the electric potential energy to the electric potential, well, the change in electric potential energy, or an electric potential, for a particular, over a particular space is equal to the change in the electric potential energy of the test particle as it moves through that gap divided by the charge of that test particle. Let me write this in a way it can upright, such that hopefully it will stand out better, that the change in electric potential is equal to the change in electric potential energy over that gap, over that path between those 2 points, divided by the test charge that's moved. Or, if I know the change in electric potential, and I want to find the change in electric potential energy, the change in electric potential energy of a charge Q moved through an electric potential is equal to Q delta V. Now we're finally getting to where these connect. Let's see, so I want to find out, okay, well, how can I write the electric potential in terms of the electric field, or the electric field in terms of the electric potential? Okay. Whoops. Let me change these colors again so that hopefully you're looking at this on the image. Using different colors hopefully makes it stand out more easily. As we'll see in 29.2, the A level that's slightly more complicated because it uses integration. The electric field, whoops, sorry, it is the finding out the change in potential requires an integral. So it is sort of finding the electric field in the x direction is equal to, as it is up here, the negative of the change in the electric potential in that direction. I'm going to pause because 29.2 is this section, and I'll do a quick example of each in the discussion for 29.2.